Welcome back. You might be a little bit disappointed. No, I'm not Harry Potter. No, I'm not Professor Snape. And we are looking at page 394 if there is any positive in this. With my recent haircut, you might consider to be more like Dobby. And I'm okay with that. And no, we're not in Hogwarts, although it's a great place to imagine being. Instead, you are in my wonderful makeshift man cave, which is now my chemistry lab. Today we're going to continue on and look at solubility graphs or solubility curves with a little more analysis built in. So I just chose not to erase my previous graph from the previous video because it's the same one, and we're going to focus on potassium nitrate again because it makes a lot of sense. There's a lot of shifting in solubilities over a small temperature range. You may remember from last time, we know that solubility does go up as we increase temperature for ionic compounds. We're not going to go beyond 100 degrees because we know water boils at 100 and it just doesn't make a lot of sense to go beyond that temperature. We also know that the unit for solubility is a little bit different than what we're used to, in that we look at the grams of solute dissolved per 100 grams of water. Anything on that line specifically is at its saturation point. Any solid that we try to dissolve less than that saturation point below the line is unsaturated. And of course, if we attempt to add too much solute beyond that saturation line, then we may create a supersaturated solution if we heat it up or change the pressure. Let's look at an example. So suppose I give you a solution that contains 70 grams of potassium nitrate and per 100 grams of water, and that solution is at 30 degrees. So a little bit warmer than the room I'm in now. What kind of solution would that be? We can answer that very easily using our handy dandy graph. If we go to 30 degrees and we go up until we hit 70 grams of solute per 100 grams of water, you can see pretty easily that we are beyond the saturation point for KNO3. So we can classify that solution as being super saturated. That should make a lot of sense. On the other hand, if I were to ask you to classify a solution that involves 70 grams of potassium nitrate at 43 degrees, if we go to 43 degrees and we go up until we hit that curve, lo and behold, we are pretty well on the line. That's pretty rare if you think about it, to have the exact right amount to perfectly dissolve. Kind of like Goldilocks' porridge. Not too hot, not too cold, just right. This is the Goldilocks situation, and we're going to say that this solution would be exactly saturated. So pretty easy. The last kind of question I want to go through with you involves shifting the x-axis, because we can change temperature and decide how much solid will actually crystallize out of solution when we cool it. So it's not really the same as a precipitation, if you will, but it looks the same, because as you cool a supersaturated solution, you'll actually see crystals coming out as we cool it down. It's kind of a neat thing to look at. So the question is, what mass of potassium nitrate will crystallize out of solution? You know, even this solution that I did dissolve, if I cooled it down enough, we would see a solid form. What amount would crystallize out if we take the solution in B, which is at 43 degrees, and we cool it down to 20? Well, the bottom line is, according to our graph, at 43 degrees, the maximum solubility is 70 grams per 100 mils of water. As we cool it down to 20, you can see from the graph that the maximum solubility at 20 is about 32 grams of solute. So if you can imagine doing this experiment, starting at 43 degrees, we would have 70 grams totally dissolved. And when we go down to room temperature, 20 degrees, we would only have 32 left. So the answer is very easy to get. The amount that we would expect to come out of solution would simply be 70 grams minus the 32, which remain dissolved at 20 degrees. And of course, that would be 38 grams of potassium nitrate that would crystallize out of solution. So there you have it. A fairly good way to analyze solubility curves. By looking at changes in temperatures, we can analyze what portions would come out of solution in some cases, or going the other way, how much more can we dissolve? There are some questions in the textbook next to page 394, and you should try those on your own to see if you have any success based on this lesson. I hope that helped. And for now, this is Dobby or Mr. Snow signing off.